So this video is on the equilibrium constant. So it's basically, the symbol for this is going to be K, like we've seen that constant before, and it gets a subscript of EQ for equilibrium. So that's the symbol for equilibrium constant. It is a ratio of the products to the reactants, specifically their concentrations. And each of these concentrations are at equilibrium. Mathematically, each of the concentrations will be raised to the power of whatever their coefficient is. And I'll write out what that mathematically looks like in a second. So this is basically how you do the math of an equilibrium equation. How do you know with Le Chatelier's principle which way is the equation going to shift? This is the math kind of behind it. So if we're considering a basic chemical equation, okay, we have A plus B is in equilibrium with C and D. Okay, these lowercase letters represent the coefficients. Okay, just those are the parts, right, when you balance the equation. So that would be like a 2, and then this A would be like an HCl or something like that. Okay, so the little ones are the coefficients, and the big ones are the actual elements there. So there is kind of an equation for this, a pretty standard model. So the equilibrium constant is equal to the concentration of the products. So in this case, we have C, right? The brackets mean concentration, to the power of C multiplied by the concentration of D to the power of D. And that's going to all be over the concentration of A to the power of A times the concentration of B to the power of B. Okay, and this can seem a little confusing with all the letters when you first look at it. It really always just breaks down to you're going to have the products on the top, and you're going to have the reactants on the bottom. And it is important to kind of keep those things separated just mathematically. Some students get kind of confused when they start mixing together the reactants and the products mathematically. Okay. So when you're doing these kinds of equations with all the different elements, pure solids and liquids are not included. Okay, so in your equation, if you have water, H2O, you would not use that. Basically, just look at the chemical symbol, and you do not use solids and liquids that are pure. So basically, we're only going to be using gases, as well as that AQ for that aqueous. Those ones are okay. And you'll kind of see, we'll do some math examples, and that'll kind of make more sense in that aspect. Last part of the notes here before we do a couple examples would be that once you get a mathematical answer, if the KEQ is greater than 1, that means that the products are favored in this reaction. Okay, so I would push to the right. If the equilibrium constant is less than 1, that means that the reactants are favored, and that is going to push to the left. Okay. So we're going to compare our numerical answers to that. So we're going to just do 2 examples here today. So here's their first example. They will give you some kind of equation. So I have SO2 gas, and it is important to make sure you do write down the state of matter because that will affect this equation. Okay, so we have SO2 reacting with oxygen, and that's going to make some SO3. Okay, some sulfur trioxide. So it's going to give you an equation, and then it's also going to give you some concentration. So if you remember when we did solutions, right? These are all different concentrations. So how strong are the solutions? So it'll give you some information, and this is basically the base question, and it wants to know what is our equilibrium constant. So we have to set up this equation first. Okay, I'll kind of show you where we're going to kind of revert back to that AB kind of setup. All right, so the KQ is equal to our products over reactants, right? That's what we got to think about. So for this one, our products are going to be that sulfur trioxide, so SO3 with the brackets, and then we need to put it to the power of its coefficient, okay? So SO3 to the power of 2. Those are all the products we have, so that's on top. And then on the bottom, we're going to have our reactants. So we're going to have SO2, and that's going to be to the power of 2, multiplied by O2, and that's just going to be to the first power. Okay, so again, those powers come from our coefficients. And make sure you do multiply them. A lot of people forget and they just add them like the equation. Okay, products over reactants. We don't have another product here, but if we did, just for sake of example here, okay, say we have another thing, what you would do then would be multiply by that other product on top as well. Okay, we just have the one here, so we don't need that. Okay, so let's look at this actual problem here. So we have it set up. Now we're just going to plug in these numbers, okay? So it gives us the concentrations in the question. All you have to do is plug it in and then use your calculator, okay? So I'm going to plug in this 1.1 molar because that is for the SO3. So we're going to plug that in, and we're going to square it, right? Because that 2 came from the coefficient. And then on the bottom, we're going to get 0.9 squared multiplied by 0.35 to the first power. Mathematically, make sure that you do the top and the bottom separately, okay? If you just type it all in straight on your calculator, it will not work. So I always suggest students to do the top and the bottom separately. Or if you're going to do it all together, make sure you use the parentheses on the bottom of the equation. Okay, so I'm just going to do them separately, type them into my calculator here. We get 1.21 on the top. And we're going to get 0.2835 on the bottom. Okay, so I did those two separately so I didn't mess up my algebra. And then now I'm going to take that 1.21 and divide it by the 0.2835. And our final answer is going to be 4.27. There is no units on this answer. Okay, equilibrium constants don't have units on them. And the 4.27 is greater than 1, which means our products are favored. Okay, so that is how you kind of do these problems. Let's look at another example. Okay, so example number 2, we're going to have some aluminum oxide, and this is going to be a solid actually, so we'll talk about that in a second. I'm also throwing some heat in there. It's reacting with a 78.9 kilojoules of heat, and that is in equilibrium with 4 aluminum solid and 3 oxygen gas. All right, so for this equation, when we're looking at it, there's a lot of stuff that we're not going to use, okay? This is a solid, and this is a solid. So both of the aluminum oxide and the aluminum are solids. We're not going to use those, okay? Solids are not included, and heat does affect the equilibrium constant, but mathematically, we're not going to use that either. So those ones are all just going to be canceled out. So if we were going to do this question, it would just be products over reactants. And the only thing that's not a solid or a liquid is that oxygen. So what you would end up doing would be oxygen to the third power. And that's it. That's the only product. There's no reactants. That is just how you would do that question. Okay, so sometimes solids, liquids, heat, those things will cancel. I'm going to edit this question a little bit just so we can see a second example, kind of more similar to the first one, just so we get a better handle and make sure we know what we're doing. If you want to try out this question, I will put some values on the side for you to kind of try it out if you want to pause it, and I will go through this question. I'm just going to change these. It's not real, they are solid, but just for example, I'm going to put one as aqueous and one as gas, which are both acceptable. So I'll give you some values for these concentrations. All right, so at this time, if you want to pause and try it out, if not, just keep watching and I will show you how to set it up. So we're going to put the concentration of aluminum to the fourth power multiplied by the concentration of oxygen to the third power. Those are our products over the reactants, which is aluminum oxide to the second power. Okay, so that is just our setup. Now I'm going to plug in those numbers. Okay, and again, I'm going to do the top part and bottom part separately just to keep the algebra straight. If you want to do it all in just one go, make sure you put the entire top and the entire bottom in parentheses. So our top comes out to 0.0287 and the bottom comes out to 16.81. So that means our equilibrium constant, it would be equal to 0.00117. Okay. In scientific notation, that's 1.7 times 10 to the negative third. Okay. When you do these, you can get really, really big answers or you can get really, really small answers. Okay. It's less than 1, so the reactants are favored.